Okay, in 11.4 we're going to talk about Gossett and the t-distribution. So this is going to be another distribution class that we're going to use to measure things and use and find predictions of values. It's very similar to the standard normal curve, as we'll see. So in the past we found confidence intervals for proportions to be p hat plus or minus the margin of error. And so this is used for making predictions. So typically we'll say we want to be 95% confident, so we'll find a confidence interval. Proportions, let's say we want to know something. Let's say something is 60%. People say yes, like I used in the previous example. Well, that's not always going to be 60%. We're going to have plus or minus maybe 10%. So maybe it's more like between 50 and 70% of people will say yes, something like that. Now the margin of error comes from our critical value of z. So we're going to pick a confidence level, 90%, 95%, 99%. Then we look up in a table the appropriate z star for those different confidence levels, and then we'll multiply those values times standard error of our p hat, and that will give us our margin of error. Our confidence interval for means now will be y bar plus or minus margin of error. So y bar, again, we use the example of height. So the mean height might be something like 5'10", plus or minus some margin of error. So it might go from 5 feet to 6 feet, 6'8", or something like that. And the margin of error will be, again, a critical value. So something like a z star, or we'll see here in a little bit, something like a t star, times our standard of error of our y bar, standard error of our mean height. The standard deviation of the sample mean is then standard deviation of our y bar is sigma over square root of n, but as we talked about in the last section, we don't know sigma because that would be the standard deviation of heights for our entire population, which is a huge amount of people, and we can't measure that typically. It's not practical. So we're going to estimate that using standard error of our mean height, which is the standard deviation of the sample. So think small here. This might be 20, 30 people, divided by the square root of n, which is the size of our sample. So we're going to use this to estimate standard deviation. So William S. Gossett was working on samples, and he was getting, his numbers were off when he used the normal curve. And this frustrated him, so he was trying to figure out, why are my numbers off? And so he actually had to come up with a whole new distribution. And basically when you're dealing with small samples and you're trying to come up with a standard deviation for a large population, the normal curve can break down. So he came up with what's called the student's t-distribution, and we're going to see how that's going to work to estimate things when we take small samples and we're trying to make predictions on a large population. We have to add one more thing we're going to have to use to classify our curve, and that's called degrees of freedom. We'll see that here in a few slides. So basically the student's t model is very similar to a standard normal curve. The difference being, as our sample size changes, the actual model we use changes. So the solid curve below is the student's t model. Notice so the dotted line is the normal curve. Notice that the solid line here is a little fatter at the tails and a little narrower at the hump, and then fatter at the tails again. So it's a little different. And as our sample size increases, it actually begins to look more and more like the normal curve. So you can imagine, as our sample size goes from, say, 10 to 100, these tails get less fat, so the solid lines get closer to the dotted lines here, and the hump becomes wider and taller and approaches this dotted line here. So in fact, we'll see in the model, if our sample size approaches infinity or is really, really big, then it just becomes the normal curve. And it actually looks exactly the same as the normal curve, and we can use the normal curve, and the answers will be exactly the same. And this is related to degrees of freedom. So as degrees of freedom increase, the student's t, this solid line, becomes closer and closer to the dotted line. They start to look exactly the same. So let's look at an example. So we're taking data from a survey of 25 randomly selected customers. Now, whenever you see small sample, this is a pretty small sample, 25. For the normal curve, we looked at samples more like 100 or 300 or 1,000. So whenever you see small samples like this, immediately start to think, I might want to use the t-distribution instead of the normal curve. So n of 25 is pretty small. Found a mean age, so we're looking at ages here. So mean age of 31.84 years, and a standard deviation was 9.84. Now again, this is y bar, 31.84, the mean age, and this is s, the standard deviation of that sample, is 9.84. So what is the standard error of the mean? And how would the standard error change if the sample size had been 100 instead of 25? So notice we're increasing sample size. Let's start with the first question. Standard error is just the s, the sample standard deviation divided by the square root of n. So we're going to get 9.84 over root 25, which is just 5, so 9.84 divided by 5. So the standard error of the mean is 1.968. So what this means is, if we were to take another sample, we would expect that its mean should be around 9.84 plus or minus around 2 years. So the mean the standard deviation of I said that wrong. The mean age would be around 31 years. Okay, 31 years plus or minus 2 years. So people would be probably between 29 and 33, that sort of thing. Now let's see how this is going to change. If we look at 100 people instead of 25, notice 100 down here is a much bigger number. So we're dividing our standard deviation by a bigger number. So now it's only about 1 year. So now our mean age would be around 31 plus or minus 1. So now the mean ages only differ between maybe 30, 32. So you can see this starts to get tighter. So the larger the sample size, the tighter this standard error becomes. Finally, we're going, just like we calculated a z-score, so z was the mean of the sample minus the mean of the population over the sigma of the population. Our t-score is going to be y bar, so the mean height or mean age or whatever we're looking at of the sample minus the mean of the population divided by the standard error of the mean of the sample, where standard error again is s over square root of n. So we're going to know this. This is the sample. This is the sample size. And then our degrees of freedom is n minus 1. So the degrees of freedom, say in the last example, when we had 25 people, the degrees of freedom is 24. Or if we looked at the second example where we talked to 100 people, the degrees of freedom is 99. And basically, we'll teach you in the next section how you can use this degrees of freedom and well, really all you need is the degrees of freedom, and you can find a critical t-score, and you can look at probabilities. So we can find a t-score and its probability of happening just like we did with z-scores. So it becomes very, very similar. Basically, we look up, based on our degrees of freedom, we look up in the chart an area under the curve, and then that area under the curve is a probability, just like we did with z-scores and the standard normal curve. And that should do it for 11.4.